Welcome to the last unit in this Math 20-1 course. In this particular unit, we're going to solve systems of equations and inequalities. Now, we solved systems of equations back in Math 10 Common, where we had two lines that were graphed, and when you found a system of equation, you wanted to find the points of intersection of those two particular lines. So we're just going to extend that when we do linear quadratics, and then we will do quadratics in the following days. So the first type of systems of equations we're going to look at is a linear quadratic system. That's where we have a linear equation, which is a line, and a quadratic equation, which is a parabola. So if you look at this graph that they give us here on the right-hand side of this particular question, in this case, this is a linear quadratic system because we have a line and we have a parabola. So when you're solving a system of equations, what you're actually looking for is these points of intersection between the line and your parabola. And we can do that in two ways. The first way we're going to look at it is we're going to look at doing it graphically. And then we're going to look at doing it algebraically. Now, what you're going to notice is that the two equations that we're going to be looking at are y equals x squared and y equals x plus 6. So if you want to compare those equations or look at the graphs of those, what we do is we put one of the equations, x squared, into y1, and the other equation, x plus 6, into y2. And we're just going to press zoom 6 to give ourselves a standard window. And you're going to see that this particular graph, which we have on our calculator, looks very similar to the graph that we actually have in our workbook. And so what we're going to do is we're going to use the features of the calculator to actually determine these points of intersection of the line and the parabola. So we're going to go second function and trace. And hopefully by now you realize that we're going to be looking at points of intersection, so we're going to be using the number 5 feature. And so what we're going to do is we're going to scroll to the left so that we're on the parabola, but we're above where the point of intersection is, and we're going to hit enter. Second curve, hopefully that your cursor has jumped to the line, and we're going to hit enter. When it says guess, I don't want to guess, I just want to know what the solution is. We hit enter, and our first point of intersection, this particular point of intersection on the left-hand side here is at -2 and 4. So now we're going to find this point of intersection on the right side. So we're going to go through the process again. We're going to press second function and trace. We're going to choose number 5 for intersect. And this time we're going to scroll along our parabola, scroll to the right using our right arrow until we get close to that point of intersection. We're going to hit enter. It jumps to our line, we hit enter. When it says guess, we hit enter. And it tells us our second point of intersection is at 3 and 9. So this point here is at 3 and 9. So how do you know in a question if they want you to use a graphical method using your calculator, or they want you to use an algebraic method like we're going to look at in a second? If a question says solve graphically, or it says solve using a graph, then they want you to graph this on your graphing calculator and determine the points of intersection using your calculator. Any other question, if it doesn't say solve graphically or graph it, you need to give me an algebraic solution to the problem. So let's look at the two equations that we have. We know that the solutions are -2 and 4 and 3 and 9. So let's see, how do we get those solutions algebraically? So the two equations we have are y equals x squared and y equals x plus 6. You're going to notice that in this particular situation, both of these have y equals in them. That means we know what the value of y is. So if we know y has a value of x squared, that means we can replace y in our second equation with x squared. So all I did is replace this y with x squared because it says y equals x squared. So now what we're going to do is we're going to form a quadratic equation. We're going to subtract x and we're going to subtract 6. So we're going to get x squared minus x minus 6 equals 0. So now we have a quadratic equation, very, very similar to we've had in previous units. So what do we need to do? We need to factor this. We need to solve for our values of x to start with. So we need two numbers that multiply to negative 6 and add to negative 1. Well, that's negative 3 and 2. So this is going to be x minus 3 and x plus 2. Now we solve each of these for x. X minus 3 equals 0, x plus 2 equals 0, so x equals 3 and x equals negative 2. Now that's only part of our solution. Remember, in a system of equations, you're looking for a point of intersection. So you're looking for an x coordinate and a y coordinate. So I have two x coordinates. So how am I going to algebraically determine these y coordinates for these points? Well, I'm going to use the equation y equals x squared, one of our original equations. It does not matter which of these two equations you use. I chose to use the first one. Now, it says x is 3. So what I'm going to do is I'm going to put 3 in for x, and I'm going to determine that y is 9. So this is telling us that when x is 3, we have a value of 9 for y, and that indeed is one of our points of intersection. So we're going to do the same thing again. We're going to use y equals x squared, but in this case, we're going to put in negative 2 for x. Well, negative 2 squared gives us a y value of 4. So that tells us when x was negative 2, y had a value of 4. So algebraically, we came up with the same points of intersection as we did graphically. And some people will be saying, well, Mr. Kaminsky, this is like a lot of work to do this algebraically when I can just punch it in my calculator and get the solution. You're right, but there are reasons we're teaching you to solve this algebraically, because there are problems that are going to be really, really difficult to solve graphically. That'll be almost impossible to find the points of intersection just because of the complicated graph you would end up with. So in those cases, it's actually easier to solve those problems algebraically. So you have to know both methods. And sometimes one method is more useful or easier to use than the other, and you need to be able to do both situations. Now it says verify the points satisfy the system of equations. Well, what it's saying is take one of the equations you had, in this case y equals x plus 6, plug in your point of intersection. Y is 9 and x is 3. And if the left side and the right side are equal, that verifies it. So the same thing again, we're going to use y equals x plus 6. Y was 4 when x was negative 2. Well, indeed, we get 4 equals 4, so both of these verify. They cancel out. Now, whenever you write the solution to a system of equations, you can always write the solution as a set of ordered pairs. So in this case, when you're stating the solution, whether you do this graphically or whether you do this algebraically, you need to state that the solution is negative 2 and 4 and 3 and 9, that these are the 2 points of intersection. You cannot just leave x equals 3, x equals negative 2, y equals 9, y equals 4. If you leave it in that method, we have no idea which x value matches up with which y value. Because in a system of equations, we're looking for the coordinates of the point of intersection. So you've got to write your solution as a set of coordinates. Okay, now what we're going to look at next is we're going to look at what are the possible number of solutions you could get when you have a quadratic and when you have a line. So if you flip to the next page in your workbook, what you're going to notice is that they have already graphed for you this quadratic equation, x squared minus x minus 12. And what they're asking us to do is they're asking us to graph the line y equals 3x on top of this quadratic, so we can see how many points of intersection there are. Because there are not always 2 points of intersection. You're going to see that in a second. So if we take our y equals 3x, And if we're going to graph y equals 3x on this particular situation, I can do that really quickly by saying that this is y equals 3x plus 0, because they don't have any value here. Now, if we look at this, this is actually in the format y equals mx plus b. So, what we know is that our y-intercept is 0. So here's our y-intercept is 0. And our slope is 3. Well, 3 is the same as 3 over 1. So we have a rise of 3, 1, 2, 3, and a run of 1. A rise of 3, 1, 2, 3, and a run of 1. So if I actually take this, and I'm just going to use a pen, like a ruler, and I draw in this line, what we're going to notice is that this particular line, y equals 3x, has 2 points of intersection on this quadratic. So we're going to go about trying to find these 2 points of intersection, and we're going to do it algebraically to see if we can find these points of intersection. So we've got y equals 3x and y equals x squared minus x minus 12. So that means we're going to replace the y in our second equation with 3x, because it says y is equivalent to 3x. So we get 3x equals x squared minus x minus 12. So if I subtract 3x, I get 0 equals x squared minus 4x minus 12. So I need two numbers that multiply to negative 12 and add to negative 4. Well, in this case, we're going to get negative 6 and positive 2. So we get x minus 6 and x plus 2. And if we solve these for x, we get an x value of 6 and an x value of negative 2. So I'm not done. I need to find my y coordinates for these points. So I'm going to use y equals 3x. And I'm going to replace x with 6. So I get y to be 18. So one of my points has an x value of 6 and a y value of 18. Second case, y equals 3x. I'm going to replace x with negative 2, and I'm going to get y to be negative 6. So our second point of intersection had an x value of negative 2 and a y value of negative 6. So let's see, negative 2, well, graphically it kind of worked out. You're going to see when we graph by hand we didn't quite get the same value, so graphing can sometimes be inaccurate. But definitely algebraically we got the same 2 points of intersection. Okay, so now we're going to look at a different line. We're going to look at this line, y equals 3x minus 16. So it still has a slope of 3, but it has a y-intercept at negative 16. So here's negative 16. And if I take my slope, which is 3, it's 3 over 1, I go 1, 2, 3 up, and 1 over, 1, 2, 3 up, and 1 over. What you're going to notice is this line only touches our quadratic or our parabola at one point here, and it looks like the coordinates of that point, if I look at them, that set of coordinates is 2 and negative 10. So I think my point of intersection, there's only one of them, is 2 and negative 10. So I'm going to try that out. I'm going to replace y with 3x minus 16. And now I'm going to try to solve this algebraically. I'm going to subtract 3x, which gives me negative 4x, and I'm going to add 16, which gives me 0, because negative 16 plus 16 is 0. So I get x squared minus 4x equals 0. So now I'm going to take out a common factor. So I get x equals 0, and I get x equals 4. Well, we know x equals 0 isn't going to work, because we don't have x equals 0 on this, but it says x is 4. Okay, and actually you're right. If I look at this point of intersection, it's not at 2, it's at 4. and negative 10. So if I now solve for y, if I take y equals 3x minus 16, if I plug 4 in for 4 in for x, what I'm going to end up getting is I get 12 minus 16, which ends up giving me, hold on, something's wrong here. This is minus 12. Hold on, let's go back. I messed up here. I copied down my quadratic equation wrong. That's a problem. See, I make mistakes just like you guys do. So this is x squared minus x minus 12, not minus 16. So this is going to mean I'm subtracting 3x, which gives me negative 4x. And I'm adding 16, which gives me positive 4. So if I actually look at two numbers that multiply to 4 and add to negative 4, those two numbers are negative 2 and negative 2. So I actually get one value of x, which is 2. So I was right. And now if I take y equals 3x minus 16, if I plug 2 in for x, well, this gives me 6 minus 16, and 6 minus 16 does give me negative 10. So my point of intersection is indeed 2 and negative 10. See, if we do it right, we actually get the same answer as we did when we graph it. So right now we've seen that if you have a line, you could have 2 points of intersection like in the first example, or you could have 1 point of intersection. The only other situation you could have is if you had a line out here that did not touch the parabola, then you would have no points of intersection. So what we're going to do is we're going to summarize this on the next page. So it says, if a graph of a linear equation intersects at 2 points, then you have 2 solutions. If it intersects at 1 point, then you have 1 solution, and if it does not intersect, you have 0 solutions. Now, something else you want to note is that this statement down here is it says we say a line is tangent to a parabola if it has 1 point of intersection, i.e. it just touches the parabola. So if we go back to this particular graph, we're going to say that this second line that we graphed here, this line which was y equals 3x minus 16, it has its tangent. It only touches this parabola at 1 point. And so that point is actually called the point of tangency. So if they talk about a tangent point or a tangent line, they're talking about a line that has only 1 point of intersection. So there we go. That's how you graphically and algebraically find points of intersection.